All right. Good morning. How are the lab tours?
No, I just wanted to know because.
No, I'm asking them. How are the lab tours? Yeah. Okay. Good.
That was really cool. We got to see they had an agricultural drone, and we got to see it take off. They showed us, it was really cool. And then we got to see they had a jet engine, like powered one.
Cool. You have something today as well, right? This afternoon? No. No.
I think so.
No. Okay.
Tuesdays and Wednesdays.
Okay. Yeah. Okay. Cool. Right.
I think we have one next week.
Okay, this should be familiar for you in terms of your curriculum at Georgia Tech. I don't know if it still stands or there are some changes to it maybe. Maybe I forgot to highlight one more, Physics 2. So it's essentially the tree that you've been following to get to where we are right now in terms of dynamics and where you could probably be heading based on what you do in dynamics in terms of what you get to learn without dynamics, which you wouldn't be able to. Okay, so this is very important to see both from the perspective of the science and the math that is involved. Science, in particular, the physics aspects of it, and maybe you start all the way from pre-calculus in your high school, and you get on to the integral equations, integral calculus. So linear algebra. And that's leading you to differential equations. So perhaps ordinary differential equations mostly, but maybe a brief exposure to the partial differential equations as well. So this is essentially the direction which the knowledge flow is there. And if you're looking at from there, the very basics of physics, your physics 1 and 2, which have helped you to understand statics, and now you're essentially in dynamics. So all of this leads to dynamics apart from the science aspects as well. That's where you are with dynamics. And by understanding dynamics appropriately, you will be able to get on to more advanced versions like what JVR teaches, for example, the system dynamics vibrations, where you're looking at vibrations unlike the rigid bodies that we consider in our course here. You'll be looking at flexible bodies. In reality, as we already discussed, all bodies are flexible to different extents, and most definitely the flying vehicle structures are, because of the need for them to be light-weighted. Therefore, they are extremely flexible. The displacements and rotations involved are in fact quite large. And there's something that you could go probably beyond vibrations into what is known as aeroelasticity, where you're looking at the aerodynamic forces and the structural forces acting in conjunction with the inertial forces for dynamic aeroelasticity. And then you need that in turn to understand how you're going to control those motions and how you're controlling the reactions or the behavior of the structure as well into your control system analysis and design. And then you're looking at the flight dynamics as well in terms of the overall motions of the aircraft, which is essentially you're talking about the all three motions we talked about for rotation, roll, pitch, yaw, and of course the three degrees of freedom in translation. You don't see that much of a sidewards in the fixed wing, except for the gust and other things. But you know, helicopters are really good at in all directions. So all three translations, all three rotations are extremely important, and it becomes so much more complex coupling that is involved over there. And then of course you have the practical implementations that you look at the lab level as part of this overall structure of where you head from dynamics. One thing probably not mentioned, probably would be covered in your options, is the aeroelasticity that I already mentioned. Okay, so this is where we are. We have got an idea of what dynamics is, what is involved in dynamics, how it is classified, what dynamics of what all kinds of entities we will be dealing with in this course, and what could be a possibility in the future. Now that we have all of that in place, we have to get back to the tools of math. So we will revise very briefly some of the aspects of that which are directly relevant to the dynamics, and then most of the things that you would have considered in those who are based on scalar quantities. Here, because vectors are important, because you have a position vector, you have a velocity vector, you have an acceleration vector, all of which you're going to deal with both in translation as well as in rotation, and therefore you need to be aware of how to manipulate vectors. And in fact, your homeworks, which are numerical in nature, will start based on what we learned today, and hereafter for the remaining 4 weeks, every Monday and Thursday at the beginning of the class you'll be presenting one homework. So we'll have about 7 homeworks totally. So anyway, you already have something for next Monday. Based on what we learned today, you will have a homework that you'll be presenting early Thursday. That is at the beginning of the class on Thursday, right? So this is, and all those homeworks are there already uploaded to Teams, as you already know. Just ignore on the top, I would have written something about 2023 batch. So just ignore that particular line. And also in terms of, because we had only 4 students at that time, the way I was dividing the problems was different. So now you have 8. So you can appropriately divide it in your team, okay? So just for, except for those instructions, everything else is valid in those homework sheets. So now the very first thing from the maths point of view that we are going to try to revise will be the derivatives. We are more interested in the derivatives of vectors, and we already saw there's a huge difference in terms of how derivatives of scalars and vectors are taken, because unlike the derivatives of scalars, which are always the same, the derivatives of vectors will depend upon the frame with respect to which you take the derivative, and we already saw a few examples, practical examples of that, of a person walking within an aircraft and then his or her motion with respect to the aircraft, with respect to the earth, with respect to the sun, with respect to the stars are all quite different from each other, taking into account the other motions that are involved of the intermediate bodies. And such intermediate bodies will become very important in a lot of our analysis. Sometimes it will be as a part of the problem definition. Sometimes a complex motion will be given in terms of just 2 entities, but to reconnect them, you will introduce certain intermediate bodies yourself in order to make a step-by-step transition from the motion that you know to the motion that you do not know, so that you can get there. So at this point in time, all of this might seem like talking in the air, but once we get into the equation, and especially when you start working on your homeworks, you will see that the essence of what I'm talking about right now. Okay, so what we will do is we will do from where we know what we know to what we do not know. So we will start off by very quickly, briefly revising certain aspects of the derivatives of scalars, how they are defined from the first principles using limits, etc. And then we will apply the same thing for vectors, so that you're aware of the distinctions that are involved, right? So let's get going. So is this visible for you, or should we close the door? Or yeah, because I use dark background. Watch out for your fingers in the hinge. So so I use the dark theme, so it might be good. Do you want to switch off these lights as well? Yeah. Just these lights. Yeah, so we will talk about the derivatives of scalars to start with, and you know this definition already. Oh, the projector is switched off, I think. Yeah, keep it on. Let's not switch the projector off. These lights you can see if you can. Yeah. Okay. Take some time for it to brighten up. Okay. Okay, so we will start from the definitions, and while on the slides I may not have the actual notation for definitions. Remember that we will always write definitions as an equal to sign with a triangle on top of it. So this is what we will use to refer to any derivation, and so in this case we are trying to look at the derivative of a particular quantity f, which is a function of only one variable. Df dx with respect to obviously x, because that's the only independent variable. So this is what we call as the, of course here we've written it in the form of a function, but essentially this is a dependent variable. And this is an independent variable. Only one, and therefore we call it ODE, as one of you pointed out in one of the earlier classes. Okay, so now going to the basics in terms of how we define it, it's entirely in terms of the limits that are involved, and that limit is taking a small change in the independent variable, in this case only x, and therefore you're talking about delta x tending to 0. And then you have the same function defined at x and a little away from x, which we'll call as x plus delta x, and then we will divide that by delta x. So you can very clearly see a graphical equivalent of this. If you were to be plotting, let's say, f of x versus x, could be some arbitrary function like that. We are not specifying anything particular about f. This should be valid for all f of x. And so if you're looking at one particular value of x that you're interested in, and then you're looking at df by dx, you're essentially saying at some other location which is a little away from it, which we will call as x plus delta x, where delta x is a very small quantity, and then you're essentially seeing what is the value of f at that original point, and what is it at the slightly displaced point, f of x plus delta x, right? So now when you're essentially taking that difference, you see the difference in the x values is x plus delta x minus x. X cancels out and only delta x is left over here. On the top, since you don't know, you're writing it for an arbitrary function f, therefore you're retaining it as it is, which essentially means the change in the y coordinate with respect to the change in the x coordinate that you're looking at, which is nothing but the slope. So that's how we correlate the first derivative to the slope of that curve at that particular location. And in general, of course, that slope will change as you go with various different values of x. If it's a straight line, for example, then the slope remains the same. But if it is anything other than a straight line, then you have the varying value of the first derivative. So this is how we define the first derivative. And this is okay because we are talking of a dependent variable, which is a scalar quantity in this case. Okay, so you didn't need to specify how this particular derivative is taken with respect to what. Okay, so right now we are just focusing on this slide only on scalar functions. So in other words, there is an independent variable and the function is a scalar quantity. It has only magnitudes, it doesn't have any direction. Yeah.
So the delta over the equation or the equal sign is basically symbolizing that we're deriving that equation? Is that what that is?
No, this is a definition, as I said. So which means that this particular new symbol that was introduced to you in differential calculus is essentially what is the meaning of it. We are saying that it's essentially if you plot that a function f of x versus x, then you have to take two very close adjacent points x and x plus delta x, take the values of f at each one of those and see the difference, how much is the change in f for a small change in x. That is essentially what you're trying to determine. But you're doing it in the so-called limit. In other words, you're shrinking that size of that triangle to 0 so that you see exactly at that point x and f of x what is actually happening. So how is the change happening? So that's the tendency of that function, how it is going to change based on a small change in x. Yeah. So that is what you would call in geometric sense as the slope of the curve, but what you call it from a calculus point of view is that it's the first derivative, right? So any other questions on this? Okay, let's move on because we need to be on the same slate going forward, because these are kind of building structures, fundamentals, without which what I'll be talking about in the next few classes will make absolutely no sense. So let's be absolutely sure that we understand every small nitty-gritty detail of these simple fundamentals. Okay, so feel free if you don't know anything or you have any questions or doubts about anything, it doesn't matter, just go ahead and shoot it at me, because I mean, what might, once you know the answer, sometimes it might look silly, but unless and until we know something, it's okay to ask questions and to find out, okay, which is very, very important, critical, otherwise learning doesn't happen. So this is as far as the function is concerned. So then, so as I said, this is the definition that you have, which is what I wrote on the board as well. So let's make things a little clearer by taking up an example. Let's take the example as f of x being, let's say, x squared, okay. So as I said, f of x, and even the way I have drawn it, could be any arbitrary function, doesn't matter. It could involve polynomials, it could involve trigonometric functions, sine, cosine, tangent, cotangent, cosecant, secant, etc. It could involve hyperbolic functions, logarithmic functions, exponential functions, doesn't matter, negative powers instead of positive power, polynomials. So it could be anything, or fractional powers, which involve square roots, cube roots, etc. So it doesn't matter, any function. This is how the definition for the first derivative from a calculus point of view and a slope from a graphical point of view is defined. So we will take a simple example. Most of you would know directly, probably from memory, what is the derivative of this. Anybody? 2x. So for a power function like that, it's very, very simple. It's x power n, then it becomes n into x power n minus 1. Okay, and we can prove that for x power n also. But to keep things simple, let's take x squared itself. Why is it 2x? Okay, so what Nafis said is the correct answer, but we want to check from first principles from the very definition. Okay, So now we are defining as an example f of x is equal to x squared. As I said, it's valid for any f of x, but we are choosing a simple example to understand the definition. Okay. So now coming to the derivative of f of x with respect to x, though we can write it as df by dx the way I have written on the top, we engineers in particular a little bit lazy in terms of how we use notations. So we will call this by another notation as just f prime. Okay, so f prime of x, so that we don't need to put all those d's over there and the x in the denominator. So we'll just call it f prime of x, right? So if you want that f prime of x, we go back to the definition over there. That is the limit as delta x tends to 0 of f of x plus delta x. Now we have f of x given as x squared. So let's put what we already know. We'll keep delta x as it is in the denominator. We have f of x as the second term in the numerator. So we'll keep that minus sign as it is, and we can put the second term directly. So this you see is x squared. Okay. Now the first term is also like the second term, just that the value that is being given to f is no longer x but x plus delta x. So it's very clear to see that all that I have to do is to replace x over here by x plus delta x, which when I do just becomes this. Okay. And there might be a tendency to right away substitute for delta x as 0, and when we do that, if I do that right away over here, I would put delta x equal to 0 over here. It becomes just x squared minus x squared becomes 0, and delta x in the denominator becomes 0 as well. It becomes 0 by 0, which is an indeterminate form. Okay, so which is why I have this warning at the bottom, which is again something that I mentioned over there, and the warning is ensure not to substitute for delta x too early when you're doing this, because that's how limits are calculated. You must be familiar with it from pre-calculus. Just more of a refresher now, because that's very, very critical for what we are going to do. Okay, so if you do, you will get something like 0 by 0 or infinity by infinity, etc., which are indeterminate kind of quantities that you will not be able to work with. So you try to simplify this and then see if you can implement this particular limit of a quantity going to 0 or whatever it is, right? So now if we want to do that, we know a simple expression for a plus b the whole squared as a squared plus b squared plus 2ab. So we will use x as a, delta x as b, and expand that out. And when we do that, we have x squared plus delta x squared plus twice x times delta x minus x squared is what we have in the numerator, and we continue to have delta x in the denominator, and of course the limit that we started out with. Okay, now we have some hope, light at the end of this tunnel over here, because we see x squared and minus x squared, which can cancel out, and both the terms, remaining terms in the numerator, have a delta x factor, and there is a delta x in the denominator, so I can cancel that out. So here one delta x goes with this delta x, and here because there's a delta x squared, it's the square which gets cancelled, and you have only delta x remaining. Okay, so the just to rewrite that, all that you have is limit as delta x tends to 0 of what remains there is delta x plus 2x is all that we have, right? Because the denominator has cancelled out, become unity, right? So that's all that we have, and now it's very easy to substitute for delta x as 0, and when you do that, you get what Nafis so easily pointed out, and we took so long to get to that. Okay, right? But there's a point to it, because we had a very simple function. It was this looked like unnecessary, monotonous way of trying to find it out, but even the fact that for any polynomial x bar n, it is n into x bar n minus 1. So in other words, if you had f of x as x bar n, then f prime of x would be n times x bar n minus 1 that you're very familiar with. We can actually derive using a very, very similar kind of a formula, but it becomes a little complex because you'll have to use some kind of certain aspects of mathematics in terms of how you get to proofs from what you know to what you do not know. So we'll not revisit all of those aspects. It's just for you to understand or refresh whatever. If you're still uncomfortable how this works, then I would recommend you to go back to your pre-calculus books, because I think all of that is something that you would have already studied but probably not used often enough and therefore forgotten, right? So this is as far as that is concerned. So once again, I'd like you to remember this, because again, for example, you could have a function like sine x by x, where the limit is let's say again delta x tending to 0. You would see that sine x sine 0 goes to 0, whereas the x also goes to 0. So it's once again an indeterminate form like this. But you can prove that using the same approach, the limit when you take as this x approaches 0 would become actually unity rather than something to be worried or concerned about that you don't know the answer for, right? So this is the notation that I already introduced, that instead of writing d by dx of f of x, we will simply write it as f prime of x. This is okay when you're looking at one-dimensional space, or what we will call as rectilinear motion, which we will introduce shortly, which is essentially the motion which is happening either on a straight line or on a curved line. So rectilinear is of course on a straight line, and curvilinear is on a curved line. So you can think of a train track or even a road which is curving. You see that you know that if there are no intersections to that road or intersections to that track, you have to go through that particular path. So this could be a road which is curving around like this, maybe even a hilly region where it's even going up and down as well, doesn't matter. But essentially this is a single path that you have. There's no other road or track which is intersecting this, and therefore the only way you can go if you're following the rules appropriately is to go on that particular dotted line that you have, right? So if you're going on that, then you can introduce a coordinate, let's say s, which is the distance covered. You could arbitrarily choose some particular location as s equal to 0, and from there you start measuring how far you have gone from that particular point, and essentially this becomes like a one-dimensional motion. You might see that this is how, if you're looking at x and y, you're actually seeing that it's having a change in both x and y. It might look like two-dimensional motion to you, but because you're constrained to move on that road, or you're constrained to move on that track, therefore there's no choice for you but just to be on this. And the same thing applies to the example that we talked about earlier. If you had, let's say, an inextensible string and a simple pendulum, and it's a planar pendulum, then you're essentially talking about that bob, or the center of the bob at the bottom, its center of mass is having a particular position at any given point in time. If you freeze the time, it's at a particular location, which I can know by just knowing this angle theta. But if I want to use Cartesian coordinates for it, I have to know x, I have to know y. Okay, it might seem like it's like a 2 degree of freedom problem, because I need to specify at least 2 values in order to determine it. But those x and y are related to each other because of the assumption that we have made that this is inextensible. In other words, its length is not changing. Okay, which is not true, because all rods are flexible, like all bodies are flexible, and there will be a little bit of flexibility, but you can have a reasonably high stiffness rod which in which the deflections are negligible, and therefore you can think of these two being correlated. So x and y are related to the length of the string or whatever you are attaching, and then of course the angle that is measured, and therefore this is just a single degree of freedom if it's a planar pendulum. On the other hand, if it's a spatial pendulum, then it has 2 degrees of freedom because it can move out of the plane as well as within the plane, and therefore it essentially has 2 degrees of freedom. Now if you also introduce the fact that this rod is flexible, then it becomes a 3 degree of freedom problem. So either you can use x, y, z, the Cartesian coordinate system, or you can use theta 1, theta 2 to theta 1 in this plane, theta 2 out of the plane, and you can use the lengthening which you can call, let's say, z. So you have a theta 1, theta 2 and a z, so you have again a 3 degree of freedom system. It's up to you as the analyst. You have the freedom to choose whether you want to choose theta 1, theta 2, z on the one hand, which might be an easier way to do a lot of your derivations, or you choose x, y, z if you're more comfortable with your Cartesian coordinates. Doesn't matter. At the end, if you're consistent with the derivation, you should end up with the same result. In other words, what is it that we are interested in? Where is this bob at any given point of time? What is its velocity at any given point of time? What is its acceleration at any given point of time? These are the kind of things that we want to determine as dynamicists when we are analyzing a particular system. Okay, so which is what we will do as part of this as well. But once you have, just like in this case, in a planar pendulum with inextensible rod, you said that it's only 1 degree of freedom theta. Similarly here, even though you have a curved path and whose altitude might also be increasing because it's the same road on which you're going or same track on which the train is going, therefore you're having only 1 degree of freedom s, because that you can determine the function of that for in terms of the curve that you're having in terms of your xyz coordinates. So if you know the xyz coordinates, they cannot be independent. If I choose some, and so this could be a 3-dimensional space xyz. So if you throw an arbitrary number for x, y and z to me, let's say 3 kilometers, 2 kilometers, 1 kilometer, and I take from wherever I have chosen as the origin 3, 2, 1 and I go there, that may not be a part of that road. Okay, so because of the way that road is designed, and because of the terrain that it has to traverse, therefore there is a correlation between x, y and z. So far we have been talking about time and x, y, z, 3 spatial variables and 1 temporal variable, 4 independent variables. But in a problem like this, the spatial variables are getting correlated with each other, so you have to be a little careful in how you specify the problem because of the constraints that are coming in. The constraint here is that the vehicle has to be on the road. It cannot just fly off, or it cannot maybe the driver is drunk and he just goes through the barricades and goes off the road. All those possibilities are there, and in fact as dynamicists we can work out such slightly more complex problems as well. But to start with, we are interested in simpler problems, healthier driver going only on the road, and therefore we know this correlation between that. So this is what is called as a curvilinear. So this is a 1D example of a 1D curvilinear motion. Remember, dynamics is all about studying motions of different kinds. And this is one example. So it's a simple example because you're having only one spatial coordinate to deal with, which is s, right? Now, of course, in turn, s is correlated to x, y, and z, but that doesn't matter. We know the path, then we know that, and therefore we are only bothered about s. So any quantity that we are talking about, let's say there's a car or some vehicle which is going over there, and that you can always get from the origin. You can draw what is called as a position vector, which we will call as r, and that position vector will be a function only of s, right? So if you specify you have gone a certain distance on this road from a particular location over here, which we have taken as the datum s equal to 0, then we know that what is the xyz coordinate with respect to a particular chosen frame of reference, which we can call, let's say, as frame A. Okay, it could be a body, it could be a building, it could be anything on earth which is kind of fixed, or it could be another vehicle. Let's say a police vehicle is tracking you, and you have a radar, and you know how this motion, they have a radar and you have a radar detector, and so you can essentially think of the relative motion between them. So A need not necessarily be a frame which is fixed to the earth. It could be fixed to another vehicle which is trying to track you, or let's say you're tracking an aircraft from ground vehicle which is moving. So all these possibilities are there. So but whatever it is, the significance or importance of this observer or the observer fixed reference frame can never be downplayed, because without this we are pretty much at the grace of nature in terms of determining this. Is very, very difficult or impossible even for most problems. So we need to understand what is the observer, how is the observer's motion, if at all there is a motion, and we have to look at the motion of the object of interest with respect to that particular motion. So it's what we are actually looking at is the relative motion rather than the absolute motion most of the time. Okay, so for example, any vehicle that you're tracking on Earth, obviously you're not taking into account the Earth's rotation, the Earth's revolution around the sun, the solar system drifting within the Milky Way galaxy, the Milky Way galaxy drifting, and the universe growing. All those complications are unnecessary. You just fix your reference point, but and the reference frame, and then reference point being the origin. Of course, we can call it as O, some origin O. And so any problem that you're tackling in your homeworks also, I want you to start off with either one or a few reference frames, because you have to tell me with respect to what you're considering the motion and whose motion you're considering. You will have at least 2 frames of reference associated with that, and you will introduce coordinate systems associated with that. You will introduce unit vectors associated with that. For example, tangential to the x coordinate, you will have the vector I, let us say, and let's say you have a vector j which is tangential to y, and k which is tangential to z. I could have just said parallel to x, y, and z axis in this particular problem, because I have x along a straight line, y along a straight line, z along a straight line, which is what René Descartes, the guy who's made fun of, as I said yesterday, introduced. But one of the few things that he understood, which we continue to use, is the Cartesian coordinate system, and that has straight lines, right? And that's where the word linear comes from, and we call these kinds of systems as rectilinear, right? And recti is the same root word which goes into the other word that you're familiar with, rectangle. So essentially you're talking about all 90 degrees and hunky-dory straight lines, that kind of a simple kind of a thing. Straight line is what comes from the linear aspect of it. Recti essentially brings in the orthogonality of the lines which are involved as the borders of the rectangle. But now remember, we are not talking of a rectilinear, we are still having the linear part, but we are talking of a curvilinear, okay? So we are willing to make these straight lines instead as curves. So I could have, instead of x going along a straight line like this, the way I've drawn it's already looking like a curve. So essentially you could have something like this, along which x is measured, something like this along which y is measured, and something like this along which z is measured, okay? So that is also a possibility, okay? Then we have what is known as a curvilinear coordinate system. So can you have anything and the way, however you like it, is it, or is there some constraint? Yes, there is some constraint, because you cannot, for example, have all of these curves on the same plane. If you have everything on the same plane, then they are not independent of each other, and you cannot get the motion variables which are perpendicular to that plane on which all of these are. So they cannot be what is known as coplanar, right? So coplanar is something that is a no-no for the kind of systems that we introduce, the coordinate systems, or in particular the x, y, z curves that we are talking about. Okay, so they cannot be coplanar, and they all obviously cannot be collinear as well. In other words, they cannot be parallel to each other. Okay, so but they need not be what we started off with, which is orthogonal. So orthogonal is what we started off with, which is why we have a rectilinear system or a Cartesian coordinate system, which is the simplest form that most of us use for most purposes. But in certain situations, we might need to give up on the straight line curves for x, y, z, and we might want to use a curvilinear kind of a coordinate system. But when we do, we have to be a little careful here, because we've been doing this so often. We might always make sure that x, y, and z mutually orthogonal to each other, and therefore none of them, all three of them are not coplanar. Any two of them obviously are coplanar. Okay, so any two vectors for that matter, leave alone unit vectors, you can move them parallel to each other if they remain the same vector, and then you can see that essentially they form a plane. That plane could be not necessarily parallel to the floor and the walls and the ceiling, etc., but nonetheless you can always find that. But if those two are coinciding, even if they are of different magnitudes, then you essentially are having what is called as collinear, which we said is a no-no, right? Now, once you have introduced two, which need not be at right angles to each other, which can be but any non-zero angle that you choose based on what is convenient for your particular problem, then the third one cannot be chosen on the same plane. If it is chosen, then it's not independent, because I can get this vector in terms of this vector and this vector. So it's like the very simple example is when I know I, the vector, unit vector I and unit vector j, any vector in that plane can be represented as x times I plus y times j, right? So you can get any particular vector. But once you have chosen two of them, the third one has to be away from that plane within which it is there, so that it is independent. The choice most people do is take perpendicular to this, but not necessary. It can be at any other angle also. It just should not be at zero to the plane. Okay, so this is essentially what the three unit vectors that you choose, I, j, and k in a general problem. And because it is curvilinear, now I'm using my fingers in a straight manner, but it can be curved like this as well, right? So in other words, at different locations, the tangent to that, because these are all unit vectors, so the magnitude is always one. It's only the direction which is changing, okay? And that direction is always tangential, just like what we talked about over here. It's tangential to that path, and therefore it can vary as a function of x, y, and z. So here, the way we have introduced I, j, k, they are constants. Okay, they are not as x changes, y changes, or z changes in the original system that we had. I, j, and k are constants. But in reality, you can introduce, and sometimes makes the problem derivation very simple, that you have I, j, and k as functions of x, y, z. That will make the problem solving much easier. Okay, but these are for more complex problems. We will take it step by step with simple problems. Yes.
I guess maybe this is a question for teaching then, but if you have a curvilinear coordinate system, how do you determine if those like I, j, and k vectors are in the same plane if their direction changes?
It's the same methodology. Remember, we talked about the Kronecker delta yesterday. So you're essentially dotting those two. So if you dot those two, and you know that it is going to zero, then obviously it is perpendicular, or the cross product. So the dot and the cross products are always a good thing to check between your I, j, k, and to see whether they are following certain requirements. Okay, so essentially if they are parallel to each other, like for example if I and j are parallel to each other, and you let's say take the cross product, you will get zero, right? So that's a no-no. You cannot get a cross product as zero. So that's essentially the thing. Or another way to check is let's say you have already defined I, j, k and want to see if it's a right set. Can you continue with it? So then you can say, try to get j in terms of, or any one of them, any one of the three, in terms of the other two. Suppose I take j is equal to c1i plus c2k. Okay, I should be able to solve for c1 and c2. Then it is coplanar, and therefore no, that I cannot go ahead with that choice. But if I cannot do that, I cannot find a c1 c2 which can make give me I in terms of j and k, or any one in terms of the other two, then that is a right choice. So because it's not coplanar or core. Yeah. Yeah. Okay.
I'd just like to be, I guess, as specific as possible. What is the difference between X, Y, Z, and I, J, K?
Very good point. Very good point. I like that. So, see, yeah, let me just erase this a bit and get to your list. Okay, the answer to your question is independent of whether it is Cartesian or whether it is linear, rectilinear or curvilinear. So let me take a simple example which you're already familiar with, which is just the Cartesian coordinate system, right? So I have x along this, I have y along this. To keep things simple, let's start with a two-dimensional entity, which is having x and y, and is having this I and j. We wanted to know the difference between I and j with x and y, right? Now, remember that the x and y are what are called as measure numbers. They are scalars, okay? So your x and y why are they measure numbers? If I take any arbitrary position vector, let us say r, okay, to a particular point from the origin O to some point P that I want to determine the position of. The same thing can be extended, as I already said, to a three-dimensional thing, but just to illustrate on the board, I'm talking about just a two-dimensional curve, okay. Now you can see that this point P is given by that set of coordinate measures x and y, right? Because let's say the origin is 0, 0. So you're going a distance x along the x-axis and a distance y along the y-axis to reach that particular point. Now this is a position vector, and therefore it has magnitude and direction, and since one direction is important there, I am underlining it using a single underline. Okay, in most books you will see this as a bold font. Or you can see, probably some cases a vector is drawn on the top. So in other words, this is one notation for a vector. This is how I will be writing throughout this course, and then maybe in some of the slides I might have this just to be consistent with some of the things in your book as well. And most books will have this in a bold font, okay? So without any underline or overline vector, it will have like this. Of course, I'll be wasting a lot of my marker pen ink, so I would rather not use this when I'm either writing on a paper or on the board, right? But these are common things that you do when you're handwriting these things, right? Now, so x and y are the measure numbers. Why? Because this position vector r can be written in this particular system as x times I, because I'm going a distance x along I, because this vector p can be thought of as the sum of two vectors. There is this one vector along the x-axis and another vector along the y-axis. Now this vector along the x-axis is going a distance x along the unit vector I, so it's x times I to get to this vector, okay? Now, to be more precise, let me call this as Q. So what we are saying is that your OP, if you're thinking of it as a vector, is given by OQ going from O to Q, and then you're going from Q to P. Okay, so this is something easy to remember because the starting and the ending points should be the same. In between, you can introduce any intermediate points. So just like we have introduced Q here, I can introduce R, S, T, many points as well, and make it a sum of many things. As long as the initial point is O and the final point is P, this will always hold, okay? And it will hold even in a three-dimensional or any n-dimensional kind of a domain as well. Now, the reason why this is called a measure number is because now this OP, which is what we want to find out as this is your R, and your OQ, we already said is X times I. And if you look at QP, going from Q to P, you're just traveling parallel to the y-axis by a distance y, and it is parallel to the unit vector j, right? So therefore you have it as plus yj, right? So now that is what this is equal to because of this particular thing. So this is implying this, right? So now if you're looking at this, you see that there are set of unit vectors whose magnitudes are 1 by very definition of unit vector. So your magnitude of I equal to 1 is equal to the magnitude of j as well, right? Only thing is important is its direction, because that's the only thing which distinguishes I, j, and if it's a three-dimensional space, k as well. Now, what is multiplying I and j? Those are scalar quantities, x and y, okay? These are coordinate measures, and that's why we call them as measure numbers, okay? So for this vector r, measure numbers of r. So x and y are the measure numbers of r in the ij system. Because I'm free to choose, instead of this I, j, k, I could have chosen some other I prime, j prime, k prime along some other arbitrary direction. So in this case, just k is not there, but let me choose I prime. I could choose some other vector, and along this, there it will not have any I measure at all, okay? It will have only a j measure, right? So I'm able to choose that. So this xy is not something which is inherent or a characteristic or a property of R. It is a property of R and the choice that you have made of the system with respect to which you want to measure, okay? And if I choose a different system, I will get different measure numbers. Instead of x and y, I would get x prime and y prime. So in other words, the same thing in a different system, because you're using prime for derivative, I'll call it star instead. So it could be x star I star plus y star j star. So you see that in terms of the overall sum, it should be the same, but individually each one of them, each of those vectors which are adding up will be different from each other, but the sum. So, and that goes with what I was talking about, right? Instead of q, I could use some other point r, and still this equation is valid, okay? Which is what is, that r is what is really leading to this particular equation, or any arbitrary q, r, s, t, etc. And I can have infinite ways of expressing the same vector r based on the choice of the unit vectors that you have. So coming back to Witty's question, difference between x, y on the one hand and I comma j on the other hand. These I comma j are unit vectors tangential to the coordinate measure curves. In this case, straight lines, but I'm just keeping the option open for curvilinear coordinate system. So you're talking of curves, but because if it's a tangential to a straight line, it's always the same. That's why in this case, irrespective of which location you are x, y, it doesn't matter, your I is always the same. Okay, it's always going to be parallel to the length of this particular board, and y is always going to be parallel to the height of this board, right? So I'm sorry, j is going to be parallel to the height of this particular board. So whereas when you have a curvilinear kind of a coordinate system like what we saw here, that I, for example, will keep changing, right? It's tangential to this. Similarly, your j will be remaining tangential. Of course, its magnitude doesn't change. It's always 1 because it's a unit vector. But as you go along the curve, it will change the direction, right? So because it changes direction, and vector can change either because of size or direction. Size remains same, direction changes, vector changes, right? So that's as far as I, j are concerned in terms of the unit vectors. So now you see these two, in terms of the very kind of quantities, these are scalar, right? Whereas the unit vectors are vectors, okay? By their very name, you can see that these are, whereas these are scalars. And again, you can see that it's scalar because numbers, you're talking of numbers there, and numbers is essentially talking about a particular sizing of something, a measurement of something, without any concern about the directions that are involved, right? So these are scalar measure numbers of R, and these are unit vectors, and both are essential in order to determine your position vector. Remember, your R is given by x times I plus y times j. So it involves x and y, the measure numbers, and I and j, which are the unit vectors, corresponding unit vectors. So it's the particular combination. Now I can write R, for example, as a column matrix x and y, okay, which you might be familiar with, vectors being written as column matrices like this, okay. But remember that I cannot just say R is equal to this, because it's that particular R, not only the choice of a vector, but also the choice of the ij's, right? And this by itself is not mentioning anything about what is the set of unit vectors I've chosen. So I could have either xy, or I could have x star, y star, right? If I had chosen the I star, j star as the unit vectors, which are not parallel to I and j, then I would have ended up with this column matrix, and this could have be entirely different numbers. Let's say this is, let's say, 2 meters and 3 meters. This could be entirely different. These two numbers need not be 2 and 3. It could be the other way around. Let's say this is 3 meters and this is 2 meters, okay? But nonetheless, if you look at the size of the vector, it will still be the same, because it's square root of 3 squared plus 2 squared. This will be square root of 2 squared plus 3 squared, and so the size remains the same, right? And if you find actually the direction might also be same. In this case, it is not, okay, because I've just chosen two arbitrary numbers. So you may not end up with the same set of numbers like that. I'm very crudely talking about certain things. But what I'm more importantly considering is that in general, x is not equal to x star, y is not equal to y star, because I is not equal to I star and j is not equal to j star. Therefore, these measure numbers will not be the same. So you now see there are many things that are important over here. One, the choice of the frame of reference, the choice of the origin, okay, because this frame can be anywhere as long as it is moving without changing its orientation. So let's say I fix a frame to this, I can move this around anywhere in the room. It doesn't matter. It would still be the same, okay, as long as I'm not changing its orientation. Once I change the orientation, anyway, the unit vector magnitude doesn't change, but its directions change. And you have moved from an ij system to an I star, j star system, and therefore your measure numbers x and y will change to x star and y star, okay. So these distinctions are very, very important. Unfortunately, a lot of people use, even professors and sometimes books will use these two interchangeably to talk of a component of a vector and a measure number of a vector. Measure number are your x, y, etc. after you choose your unit vectors. Whereas the components of the vector are this whole thing. For example, xi, that product is a component, okay. So distinguish, this is a component. So a component of a vector is still a vector, but a measure number of a vector is always a scalar, Just keep that in mind, okay? Because the component is the measure number times the corresponding unit vector, okay? So you have two components here, x times I is one component and y times j is another component, and both of those are vectors because you started off with a vector. On the other hand, we remember very briefly talked about other tensors like dyadics, which need two directions. So if you start off with a dyadic and you express it as a sum of unit vectors times you need two unit vectors for each one of them, and you will have measure numbers for each one of them. So each one of those components will be also a dyadic, but the measure numbers will continue to be a scalar. So it doesn't matter if it's a zeroth, the first zeroth order tensors are your scalars, first order is your vectors that you're again familiar with, second order is something you probably are not so familiar with but you'll use in your deformable bodies and your structural analysis course as you go to the next year, in the junior year. And then you're looking at all of these levels that you're talking about, let's say third order, even fourth order tensors, which is essentially your Hooke's law in a generalized sense will be lead to fourth order tensors. Irrespective of that, as long as you're breaking it up this way, you will be breaking it up into components. Each one of those components will be, if you're breaking up, let's say the Hooke's tensor, you will be having, each one of them will be a fourth order tensor, okay? But the measure numbers, even there, will be scalar quantities, okay? So keep this in mind, and once you have a set of measure numbers, in the case of a second order tensor, instead of column matrices like this, you will have square matrices, okay? And if you're thinking of, let's say, a third order tensor, then you will have a three-dimensional matrix, so to speak, okay? So in other words, you have rows, columns, and a set of matrices along the length of this room. So essentially you're talking about that. And it becomes more complicated to visualize when you go for higher dimensions, and which is necessary in dynamics because you have the three spatial dimensions and time, and therefore you have a fourth or order kind of a thing that you have to sometimes imagine. But we will keep things simple in this undergraduate level course. We will not bring in those concepts, but it's good to be at least qualitatively aware of those things, so that if you have such kind of problems, they can be more efficiently solved when you rope in those kinds of concepts. Is this clear, Viti? Yeah, okay. Anybody else? Any questions?
So I just have
Yes. Yeah, please.
Sir, if you have the directional base vectors itself as curved, as you said,
Yeah.
let's say for a single curve in a three-dimensional coordinate I can map. But as it comes to, let's say, planar surface or a three-dimensional body, if the coordinate itself varies, then you are every time, how do you map those?
Yeah, a very good point. So essentially you're looking at the requirement for a tangent, because how are IJK defined in this curvilinear coordinate system? As I said, it's essentially based on a unit vector, so we know magnitude. Only thing we are concerned is the direction.
Yes.
So it's the direction is the tangential direction to the curve. So first I define a curve x, which is my x coordinate, okay? Now if I want to determine I as a function of that x, all that I do is I go on drawing a unit tangent to that, okay? So I go on that curve. As the curve goes, the curve is already fixed. Now I go with the magnitude is the same, it's a unit vector. Now I keep drawing tangents at each point of that curve. So I get I as a function of x.
At that point.
Exactly, at each value of each location along that curve. Same thing I do with the other curves, which is the y curve, y coordinate measure curve. I go get the unit vector tangents to it. I get the j vector as a function of y. Now I similarly go get the z coordinate curve. First I define that according to my convenience, as long as it is non-coplanar and non-collinear. So then I have that third direction, again a unit vector tangential to that curve. I get the k as a function of z. So now I have I, j, k as functions of x, y and z respectively. So I have these sets of unit vectors with respect to which I can define any other vector, okay? Exactly, right. So this may not seem very useful when we are dealing with rigid body dynamics, but when we are dealing with flexible body dynamics, this becomes very, very critical that you introduce such kind of a system. For example, you can think of this as a beam. So now you're, let's say, bending this beam. Once it is bent, initially it is straight. Once it is bent, it is a curve. Now it might be convenient to have something which is tangential to that curve. So in fact, there is mathematical terminology for that. I didn't bring it up because it's not at that level here. It's called a covariant vector. So the covariant vector is, as the name itself suggests, co means together with something, variant. So the x curve is varying in a particular way, and this unit vector I is varying along with it, therefore it's a covariant vector. Similarly, there's something called a contravariant vector. So that you define, once you have defined the covariant vector tangential to the curve, now you get two more vectors which are mutually orthogonal to that. So then you call that set as the contravariant vector. So these become what are known as base vectors. The base vectors are the vectors with respect to which you define. So in this case, I and j are the base vectors. I star and j star are the base vectors. In a three-dimensional space, of course, you would have k star and k as well in both of those.
Understood. I just want to ask a last question.
Yeah.
It's little weird. Are contravariant always orthogonal?
Yeah, you can see the contravariant and covariant as two sets
Yes.
are mutually orthogonal to each other. But the covariants themselves, within themselves, need not be orthogonal. The contravariant within themselves need not be orthogonal. But the reason why we introduce contravariant is to take some advantage of some orthogonality principles. And with covariant alone, we cannot have that luxury. So therefore, we go ahead and introduce the contravariance. Okay. Anything else? Anybody has any questions or doubts? Okay. Let's go ahead. I think, yeah. So if the independent variable is x, or any spatial variable for that matter, and there's only one of them, because it's a, let's say, a problem like this, that it's what we call as a rectilinear or curvilinear. If this road was straight road, then we call it rectilinear. If it is curved, we call it a curvilinear problem. But only one variable is necessary, which is s, which is what we're talking about. So in either of those cases, I can talk of just a what is called as an ordinary derivative, and I write d instead of dou, right? So when I write d instead of dou, it's essentially not a partial derivative but an ordinary derivative, and in those cases I will take it as primes, okay, whether with respect to x, y or z. Most cases we choose x and we call that as prime, okay. But if more than one are there, like in this problem both x and y are there, then I would, instead of calling it as just to reduce the labor of writing, we can call it as f comma x, which is nothing but defined as a notation for dou f by dou x, and f comma y defined as dou f comma dou y. Similarly, if it's a three-dimensional space, you'll have z as well, which is dou f by dou z. And these are partial derivatives. We'll come to just revising some of those things which you might have already been exposed to briefly. And so this, we don't have the luxury of calling it primes anymore. We have a little more to write, but that's a comma and an x, okay? So it's not too much more. On the other hand, we want to distinguish, but as I said, we understand that these are all independent variables, whether it's space or time, and there's a lot of analogy, etc. But in our experience, how we experience time in our life, how do we experience space in our life, these are quite distinct. In fact, the word kala that is used, we think of time as the source of space, because if there is no time in our experience, there's no distance in our experience. The reason why I see Chinnababu is at a particular distance is because it will take me this much time to reach him. So it's based on that time, that understanding of that distance, as essentially that's the way the brain networks in order to perceive that, and therefore take it into account, right? So now, to keep that in mind, so instead of primes, as far as derivatives with respect to time are concerned, we use a dot. Okay, if the function is not depending on any spatial variables, depends only on time t, let's say, it could be, for example, this f could be s. Okay, so if I'm talking of s, which is the location of that particular, let's say, railway engine which is going on this track at any given point t, time t naught, let's say t equal to t naught, all that I have is s as a function of t. I have to substitute t naught to get s, right? So now I have that curve, instead of f I have that s of t, so I can think of an s dot of t, right? So oops, sorry, this should be this should not be x, this should be t. Okay, so this is spatial coordinate and t is the time, right? So now this is a generic definition of the derivatives of scalar functions, but there's a lot of physical relevance to it. We as engineers, or even scientists for that matter, do not do math for the heck of doing math. Okay, math by itself is beautiful for the mathematicians. We can go on a high just doing math alone, but just that for us scientists and engineers, we want to use math as a tool to model, okay? And therefore, it's just the language of science or language of engineering, and therefore we always want to look at some examples of these kinds of derivatives, and some examples are, we already saw from a graphical perspective. Slope is an example, where if you have a particular function depending on just one variable and you're plotting against that, you're essentially talking about the slope of that particular curve, which is the first derivative of that function with respect to that variable, on single variable that it depends upon, right? And to take it a little more clearly in terms of let's say a dynamic property, which is the velocity of a particular particle. So a particle is moving and we want to track its velocity. It could be a body also, then we'd be tracking its, let's say, the velocity of its mass center or some point on the body whose velocity we might be interested in. And that velocity is the derivative of the position vector with respect to time. Okay, so once again, all those definitions will go to this kind of a definition, and that's of course in the case of functions, we are talking of a scalar function, so it's very easy. We don't have to bother about directions, only magnitudes are sufficient. But once we get to velocity, velocity is a vector and is defined as a derivative of a vector, which is the position vector, which we were already talking about, like this r, the position vector r. So this particle p, let's say, has certain mass m and it's moving along, okay, because of some field in which it is, let us say, gravitational field, or it could be a magnetic dipole which is moving in a magnetic field, or whatever, electric field, or whatever. But that particle is essentially moving because of certain external forces that are acting on it. And now that position x and y are going to be functions of time, and therefore this position vector r, which is given by xi plus yj, is also going to be a function of the time. And we can take the derivative of r with respect to time. But when we do this, it's not as simple as what we did over there. We have to specify with respect to which frame of reference we are taking that derivative. And that frame could be the ij frame itself, okay? I and j can be thought to be fixed on a body A, or on a frame of reference A, which is hypothetical, not even an actual physical body. And then you calculate everything, because once I and j are fixed, it's very easy to take the derivative, because if I want r dot, it will just be x dot I plus y dot j. But on the other hand, if I and j were varying, if you take the derivative in a system, in a reference frame in which I and j are changing, so this could be, let's say, the aircraft fixed frame, and I'm taking with respect to the earth fixed frame, and anything on the aircraft which is moving around, then for example, the flap deflection, etc., those things are moving on the aircraft, and the aircraft is moving with respect to the ground. I take the flap motions not with respect to the ground, but with respect to the aircraft, because that's a very simple direct model to analyze. Then I also know that the aircraft fixed reference frame, if the aircraft is performing a maneuver, it's not just simple cruising. Then you have the directions are essentially changing. So when you have something like that, then r dot will be, remember, you know the chain rule, where you see that if you have a derivative of a product, then it will be x dot I plus x times I dot plus y dot j plus y times j dot, right? So you will have 4 terms instead of just 2 simple terms. In our case, we were just talking of I and j fixed to that frame, and we are taking the time derivative with respect to that frame. Therefore, I and j remain the same. We are only need to calculate x dot and y dot. Okay, so that's one level of complication going from slopes, which we already introduced in that graph, which I erased, and then the velocity, where you are talking of a derivative of a vector now, which is the position vector to be more precise, and which is involves the reference frame, and without specification of the reference frame, it is nonsensical to talk about any derivative including velocity or acceleration. Next is a rate at which certain things change. Okay, for example, the rate of consumption of food. How quickly is the soup getting over in your CVH table, right? So how quickly is it? So it could be volume per particular time unit, let's say per second or per hour or whatever, right? So essentially, again, you're talking about taking a derivative of a particular quantity with respect to time. Okay, and depending upon that, whether that quantity is a scalar or a vector, again, you have differences. And things become even more complicated when you are taking the derivative of not a vector, but let's say a second order tensor, etc. Okay, but we'll not overly complicate it, and which is why I kind of struck this out, because here you're talking about a derivative not with respect to a particular thing, but essentially you need two different directions to be involved over there. So there's something called the deformation gradient tensor we go to, and then come to the strain definitions of various kinds. So don't bother about this for now. Those are things that you will learn as part of the more advanced courses that you take in your junior year. And but it's an important thing to be aware of the fact that the entire world that we live in, most of the things, if you want to do a mathematical model, then you end up with nonlinear equations first of all, and those nonlinear equations are differential equations, not ordinary differential equations, but partial differential equations. And therefore the study of such differential equations, calculus involved with that, and the partial derivatives involved with that, and the nonlinear behavior of those functions, the unknowns to be determined, all of that become important. So already you understand the difference between ODEs and PDEs, as the number of independent variables is 1, then you have a ODE. If you have more than 1, you have a PDE. But what is nonlinear is not necessarily in the independent variable. Independent variables, nonlinearity could be anything. Like, for example, we took a very simple function f of x equal to x squared and tried to work that out. So that's not a overly complicated thing, because the independent variable is what was squared or not linear, right? But here we're talking of, when you're talking of nonlinearity, we're talking of the nonlinearity in the dependent variable. Okay, what we are trying to determine, that itself is nonlinear, either by itself or in terms of its derivatives. So if you, let's say, you're trying to solve for a particular vector r, that r appears as r squared in the equation. It could appear as a log r, it could appear as a sin r, etc. Or it can appear as r times r prime. Okay, that is also a nonlinearity, because both are involving r. Even though r itself is power 1 and r prime is power 1, the product of r prime makes that kind of an equation, and because r is the unknown in that particular problem, it's a nonlinear problem. So in terms of the classification of differential equations, you should always be aware. We have various classifications: homogeneous, non-homogeneous, whether you have the right hand side 0 or not. Then you have the ordinary partial, number of independent variables come into question, linear or non-linear. There a lot of people get confused that even when they see independent variables which are not linear, they think the equation is not linear. That's not true. The equation is still linear as long as all the dependent variables are appearing as power 1 in every term at the most, which means that it can have 0 as well, power 0 as well, which is a constant term, which is what makes the non-homogeneous kind of an equation. So depending upon the type of equation, there are many different ways of solving it, as you would have studied in the courses which were dedicated to that. So we will not go through all of those details. You'll have to, as and when you require it from our course point of view, you'll have to revisit that. But if you get stuck up with something somewhere, I'll probably see that when you're presenting the homeworks, and we will talk about it a little bit at that point in time. Okay. So can I go to the next slide? You're fine with this, right? Yeah. Yeah. Now in the previous slide we talked about just x function of x, right? But of course I use the whiteboard to talk of functions of x and y, etc. That's the simplest next level extension. We're talking of the number of independent variables you're increasing, okay? And in almost all dynamics problems, except for the simple curvilinear, rectilinear kind of problems, once again to tell you, rectilinear is a special case of curvilinear where the curve is straight line, okay? Now, when you go beyond the rectilinear and curvilinear, which also we will study because that's an easy way to introduce dynamics. But once we do that, we will be talking about functions of multiple variables. In other words, more than one independent variable is involved, and therefore we introduced this concept of partial derivatives already. We said f comma x is dou f by dou x, f comma y is dou f by dou y, f comma z is dou f by dou z, and f dot would be dou f by dou t in that kind of a problem, right? So f dot equal to dou f by dou t. It's a notation. These whatever is there on the left hand side are just simplified notations so that equations look compact, at least for us. We are in the comfort zone looking at it. Otherwise the same equation looks much longer and more complex when you write it out explicitly like this, but this is what we mean. So when we take these kinds of derivatives, right? So when differentiating with respect to one independent variable, all that you have to do is to keep the other variables constant. So for example, if I want to take f dot, I have to take the derivative exactly the same way which we define the derivative, limit as delta t going to 0 of f of t plus delta t minus f of t divided by delta t, which is something that you cannot substitute delta t as 0 right away, but after some simplification you might be able to do that. Then you get f dot, and when you're doing that, remember that f now can be a function not only of t but also of x, y and z in general, and therefore you have to fix x, y and z as some particular value, let's say x naught, y naught and z naught. But that particular value can actually be an arbitrary choice. You can choose something, I can choose something, somebody else can choose something else. Therefore, once you are solving it, then you can resubstitute for your x naught, y naught and z naught as just x, y and z, and you get your dou f by dou t. Just for the calculation of that limit, you are setting x as x naught, y as y naught, z as z naught, and calculating your dou f by dou t, okay? Just the way you would have calculated df by dt, because now x, y and z are fixed values, x naught, y naught, z naught. It's only one independent variable now. You're no longer talking of partial derivatives, you're talking just again, of course, it's hypothetically you're talking of a ordinary derivative, and you're trying to solve for that. When you're trying to derive that, once you derive it, you can resubstitute for your x naught, y naught, z naught as x, y and z. So that's what we are talking about over here. So here we talked about an example which involved t. Here there is no t. Let's say there are only three spatial coordinates x, y and z with respect to which a particular function is defined, and you want its partial derivative with respect to x. The word partial derivative becomes relevant only because it's a function of more than one variable. If it was not a function of y and z, function only of x, then I just write it as df by dx like in the previous slide. But now I write it as d by dx of a new function f bar of x in which y and z are fixed. But the particular choice for y and z need not be a numerical choice. I call it by some other way constant y naught, z naught. But since that choice itself is arbitrary and will always, the solution for this will always be valid whatever the value of y naught and z naught within the range in which y and z is specified. Therefore, I can resubstitute for y naught, z naught as y and z once this has been carried out with that limiting process, right? So to probably illustrate that, we'll take a very simple example over here. Okay, once again, laziness creeps in, and for most of what we will do in this course, whenever we get sign of a particular thing, we will just write it as s subscript of that argument. So if I write s subscript x, unless otherwise mentioned, the default means that I'm talking of sine of x. Okay, then plus z squared. Okay, so this is the function that is given to us, and suppose we want the partial derivatives. There are as many number of partial derivatives of a particular order as there are independent variables. So the first order of partial derivatives are first with respect to x, then with respect to y, and then with respect to z. So let's start off with f comma x, which we remember we defined as dou f by dou x. Okay, what is dou f by dou x? So this is by definition dou f by dou x, which means that it's just a df by dx, where you are setting that other two variables to a particular value. Okay, which you're not giving it numerically, but you're saying that it's a constant. Okay, but within that particular range, whatever you're interested in. So when I do that, your f becomes an f bar kind of a quantity over there, which is now equal to d by dx of exponential x. Oh, sorry, that was y, right? That would have made the taking the derivative a little more complex. So exponential x, sine of, instead of y, we have y naught, and instead of z, we have z naught, and in the function there is a square, right? So now this is what we are looking at. Now, because y naught is a constant, sine of y naught also becomes a constant. Because z naught is a constant, z naught squared is also a constant, okay? So we can treat this as a constant c1, a constant c2, and then all that I have to take is the derivative of something with respect to x. So I can go back to my original thing, taking the limit as delta x tends to 0 of this particular thing, which is exponential of x plus delta x sine y naught plus z naught squared minus the same thing with just x alone, which is this divided by delta x. Okay, so now you can expand this out and get it, but I will not go through the whole process from the definition. We already worked one with definition. So all that you know is exponential x, when you take a derivative, just becomes exponential x itself. It remains the same, right? So which means that this derivative is just going to be, the first term is a constant multiplied by exponential x. So it remains the same constant multiplied by exponential x. And the second one is a constant, so a derivative will go to 0. So that doesn't make any contribution. So this is what we are left with. And then we know that y naught is an arbitrarily chosen fixed value of y, and therefore this is valid for any y, and therefore we come and say that this is actually equal to just exponential x sine y. We don't need to put the y naught any longer. Okay, so same thing. If so in this particular case, just like we fixed y naught and z naught, y and z as y naught and z naught, similarly you want to take the partial derivative with respect to y or z, you have to keep the other two constant, and then you can go about doing that. Okay, so that's one aspect. The other aspect is a concept called total derivatives. Okay, and this is something that you will see often in dynamics problems, that you have a particular function. Let's say the position vector is a function of x, y, z and time, but x, y, z themselves are functions of time as well. Okay, so in other words, there's a level which is within the original level, and that's something that is kind of a nested kind of a structure. So when you have a nested kind of a structure like that, so yeah, I think it's already written here. So f of instead of just f of t, you have f of x, y, z and t, but x, y, z themselves in turn are functions of the time t. This is somewhat similar to the curved path that we were talking about, let's say the rectilinear or curvilinear path that we have. On that, we know the position of a vehicle, and we know those positions as a function of time, and it could have an explicit dependence on time as well. So this last thing is talking about an explicit dependence on time, and these three are what are known as implicit dependence on time, because it's depending on time but in an indirect fashion, which is why it is through x, y and z it is depending on time. So the total dependence of f on time is not only because of its explicit dependence, but also you have to account for the implicit dependencies. So what you do is, as usual, you take a dou f by dou t, that is one of the terms. So that is already anyway there. But in addition, you also take the chain rule and say because f is varying with respect to x and x in turn is varying with respect to t, therefore I have a dou f by dou x times dx by dt. Why I am not writing dou over here and d is because x is a function of only one independent variable time, and therefore I can afford to write it as dx by dt over here. Similarly, you have a dou f by dou y times dy by dt, and because of the change in f with respect to z and the change in z with respect to time, you have these terms. So now you have this total thing, and I think this is again a mistake. So small, usually we use uppercase d for this to distinguish from dou f by dou t, but since you have a partial derivative and ordinary derivative here, it might be okay, but it might be a notation from some books. But here we are talking about a total derivative, and usually you put it as uppercase df by uppercase dt. So this is how you write it, as the total derivative. Okay, and this need not always be time. It could be any kind of a parameterization you have. For example, we're talking about this simple pendulum problem in which theta could be the parameter. So I can put your x as a function of theta, y as a function of theta, and if it's a spherical pendulum which is moving out of the plane as well, then you can have z as a function of theta as well, and there might be some explicit dependence on theta also, depending upon what variables we are talking about. It could be the position, velocity, acceleration, whatever, right? So when you have something like that, then you have to deal with taking the derivatives in a chain rule like this, one explicit and the others implicit, and then combine both to get the total derivative, which is what will be essential for defining a lot of problems. This is one more thing in terms of notation, which I find even a lot of graduate students and even professors tend to use it very lax. I'm sure will be familiar from school, middle school, of this board mass rule, where you know you have to take the do the subtraction, addition, multiplication, etc. in a particular order. But in terms of bracketing also, remember there are many different types of brackets, of which these 6 are very common: the square bracket, the flower bracket, the circular bracket, the angular bracket, the underline bracket, and the overline bracket. Okay, so when you have something nested like this, for example, this is a wrong way to write this, because I'm using for this outer bracket also circular, and the inner bracket also I'm using circular. I cannot do that, okay? Strictly speaking, mathematically speaking, I cannot do that because it always creates a confusion whether I'm opening this bracket, closing this back. You have to look very, very carefully in order to understand this is one set and this is not a part of that set, this has to be a part of this set, etc. It makes it very, very difficult to visualize that. So therefore, you do it in this particular way. For example, I could have all these t's, I could have put it in any bracket which is within the circular bracket. I could have used, let's say, an angular bracket, I could have used an underline or an overline over that, and I could do that. Or I could have changed this outside bracket that is there, instead of circular, I could have used either a flower or a square bracket, then it's good. So if you just imagine this is a square bracket and this is a square bracket, rest remains as it is, then you can see visually very clearly that you are distinguishing which bracket is opened when and which is closed otherwise. It's not a major deal, but this is a convention which is a very strict mathematical convention, which unfortunately most scientists and engineers tend to ignore. But if we do, then it will be to our own advantage that we can very clearly visualize how things are getting nested within each other. Okay, are there any questions, doubts about this? Yeah.
I've learned that the square brackets go in front of the braces. And square braces.
By front you mean outwards or inwards?
Like, so you have it as the square brackets and then the braces and then
Yeah,
the regular
yeah, yeah,
parentheses.
yeah.
I've learned braces, square brackets, then parentheses.
I see. Okay, okay. There might be a few changes in convention. So there are different kinds of systems. Typically, some essentially coming from a British kind of a system. Again, within British, see, there's also a lot of this from different kinds of universities. The kind of thing it comes, like Cambridge would have come up with something, Oxford would have come up with something. So there might be subtle variations. It's a question of maintaining that consistency in whatever you do, a particular document. You don't mix and mix those up. So it might be true. I'm not aware of that, but it might be true. Yeah, the reason why this seems more natural to me is because, for example, if you're thinking of matrices in your linear algebra course, you use square brackets for, let's say, a square matrix or a rectangular matrix. But for column matrices, you use flower brackets. And you can think of a square matrix as a set of column matrices. Like, for example, if you have something like this, right? So this is a square bracket. This is whenever you have a rectangular matrix, you always use square brackets, right? This is a convention that we typically follow in linear algebra. But on the other hand, if I was writing just that, the first column alone, I would use these flower brackets. So now you see that this is going into that, okay? So which is what I think is a little more natural, but for some other reason, maybe for some other important reason, they could have probably interchanged those two. So what we are saying is, in this case, for example, if it was, let's say, 3 plus x over here, then when I put 3 plus x, I could use any one which is within that. So for example, I could use a circular bracket over here. So that's how it works. And if there's something within that as well, then I could probably use angular bracket, underline or overline. Okay, so it'll be nice if you start practicing some of these in your assignments as well. I'm not going to hold you very strictly for that, but whenever you find some nesting is happening, if you can see that you ensure this kind of a distinction between the levels, various levels of nesting, then it will be good, because once we make it a habit, then when we are writing papers or we're writing something else, it becomes almost natural muscle memory for us. Any other questions on this? On the total derivative, on the partial derivative? Because till the previous slide we were talking only about ordinary derivatives. Okay. Next, once again, we want to start from scalars and take this carry it over to the vectors. This might seem too trivial for you, the commutative nature, associative nature, etc. But once you understand this for scalars, it's very easy to appreciate the same thing happening in the case of the vectors. So for example, the sum rule, if you have any two quantities A and B, you can either add A to B or B to A, right? So in other words, that's the commutative nature of that, and because of which the derivatives also follow the same thing. So and I think in fact we use that over here. So for example, we already used that in this particular example. We wanted the derivative of the sum, but then we took it as the sum of the derivatives. Okay, we took the derivative of the first, plus the derivative of the second, which was 0, and then we added up. We didn't have to do all of them simultaneously. So it helps in actual implementation or actual derivation of these quantities. Might seem very simple, but the power of how it helps in making our solution process efficient is something that we should be aware of and utilize it. The next thing is, instead of sums, you have a product. It's the same two functions, f1 and f2. Instead of adding them up, you're having a product. And in fact, that's again something that we already utilized in this particular case, where we say that you can take the derivative of one of them at a time, keep the other the same. Okay, so you take f1 of x as it is, take the derivative only of f2. Then you do it the other way around, and then you have both those terms, and then that helps simplify a calculation of lots of derivatives. Though many people you call this as chain rule, this is more strictly speaking. Sometimes I make the mistake of calling this as the chain rule as well, but this is essentially the product rule, and this is the chain rule where doing the nesting. Okay, so once again, this is wrong. I should not be using the same kind of brackets both over here, right? So here, when we're talking of the chain rule, we have a function of a function. Okay, so then how do you go about doing that? You say you first take the dg of dh and then h prime of x. This is something very similar what we did in the total derivative case. When we calculated df by dt, we said that f depends on x, for example, which is also a function of time, and therefore we took df dou f by dou x and then dx by dt, right? So something very similar to that is what we are talking in a more generalized term over here, right? And you could of course do an example for this. Would you want me to work it out, or it's quite trivial, simple, right? So it should be fine. So you could use, because in this particular example you see that there is a product, there is a sum, and there is a nesting function. There's an x squared. So all three rules will be actually utilized in order to calculate that derivative. Okay, next is we want to take that whatever we saw for scalars, we want to take it forward to vector functions. Okay, so we do want to do that. Let's take an example of a vector v, which is a function of a scalar quantity t. So pretty much in the entire course, we will be talking only of, whenever we talk of vector functions, we'll be talking of a vector which is a function of scalars, not a vector of